Well, hello everyone. I'd like to welcome you to Mr. Schaaf's classroom today. We're going to be talking about thermochemistry, and in particular we're going to be looking at the difference between endothermic and exothermic reactions. So let's just jump in and get started.
Ready or not, here comes science. It might be choice, here comes science.
Okay, so let's get started on endothermic and exothermic reactions. So the very first thing that we're going to look at is what happens when delta H is positive. So now remember, delta H is the enthalpy of the system. And so when delta H is positive, the heat is being absorbed by the system. So our system is gaining heat being absorbed positive. That is called an endothermic reaction. When delta H is negative, the heat is being released by the system. So the system is giving away heat, making it negative. That's called an exothermic. So exo, given away, endo, taken in. So here's some examples of that. So when you have a chemical heat pack that contains iron filling that are oxidized, it's an exothermic reaction. So what you're going to feel is your hands are going to get warm because of that release of heat. So the system is releasing heat into the surroundings, which in this case are your hands. Then you have cold packs, which are ammonium nitrate that is dissolved in water. So we take ammonium nitrate, we put it in some water, and when it dissolves, you have an endothermic process that happens. Your hands are actually going to get cold because the system, in this case the test tube, is taking in heat from the surroundings, and you're going to feel it getting cold. So those two in particular we're going to see in the lab as an example, or at least the ammonium nitrate, and then I have a different one for the exothermic process. So let's just kind of summarize up enthalpy. So the values of delta H for a chemical reaction is the amount of heat absorbed or evolved in a reaction under conditions of constant pressure. Okay, so in other words, how much heat we're going to absorb or give away to our surroundings. An endothermic process has a positive delta H and absorbs heat from the surroundings. An endothermic reaction feels cold to the touch. An exothermic reaction has a negative delta H, gives off heat to the surroundings, and it feels warm to the touch. For an exothermic reaction, the surrounding temperature rises due to the release of thermal energy by the reaction. This extra thermal energy comes from the conversion of some of the chemicals' potential energy in the reaction into kinetic energy in the form of heat. And we'll actually, again, be measuring this in the lab by taking the temperature during a reaction and seeing how much release of energy we have take place. During the course of the reaction, existing bonds are broken, and new bonds are made. The products of the reaction have less chemical potential energy than that of the reactants. So again, that should make sense because when we're looking at the reactions, they have the potential to react. Once they react, of course, you're going to have less potential energy. The difference in energy is released as heat. So that energy difference that you see, we see it in terms, or can measure it in terms of heat. So now for an endothermic reaction, the surrounding temperatures drop due to the absorption of some of the thermal energy by the reaction. During the course of the reaction, existing bonds are broken again and new bonds are made, same as if it was an exothermic reaction. The products of the reaction have more potential energy, chemical potential energy than the reactants this time. So be sure you see the difference there. Now the products have more potential. They've gained chemical potential energy. The next one is to acquire this extra energy, some of the thermal energy from the surroundings. So they got that energy from the surroundings is converted into chemical potential energy and stored in the products. So let's take a minute and just think about it. If you have an endothermic reaction occurs in a flask, what's going to happen to the temperature of the flask. In other words, what are you going to feel? Because that's how you're going to measure it, is what do you feel? Think about it. And hopefully you thought the temperature would fall. So again, an endothermic reaction, the flask is taking from the surroundings, so you're going to see a decrease in temperature of the flask. Okay, so what we're actually going to be doing with this is some reactions. And this is going to be very similar to when we did our mass-mass reactions, when we were doing limited reagents and so forth. So kind of keep that in mind as we are talking about this piece. So the enthalpy change in a chemical reaction is an extensive property. If you'll remember, extensive properties depend upon the amount of mass. So the more reactants you use, the larger the enthalpy is going to be. So by convention, we calculate the enthalpy change for the number of moles. So again, things have to be in moles of reaction in the reactants as written. So you're going to see this reaction here, and it shows you that you've got pentane. So we've got a combustion reaction going on here. It's reacting with oxygen. It's going to form carbon dioxide and water. So one of the things that we're really going to be looking at here is the mole ratio. So again, we have 1 mole out in front of our methane for this amount of heat energy, a negative 2044 kilojoules. So it's a relationship, a ratio if you want to say. So if we have 5 moles of oxygen for every negative 2044 kilojoules, we have 3 moles of carbon dioxide for every negative 2044 kilojoules. And we would have 4 moles of water for every negative 2044 kilojoules. So again, just like when we did mass, remember mass, we'd say for 5 moles of oxygen, you produce 3 moles of carbon dioxide. Very, very similar you're going to see in the reaction process. So keep that in mind. Okay, so let's go ahead and start our first problem. So the first thing that we're going to look at is, it says ammonia reacts with oxygen according to the reaction or the equation. 4 ammonia plus 5 oxygen makes 4 nitrogen monoxide and 6 waters. Now remember, the heat of the reaction here is a negative 906 kilojoules. And for what we talked about earlier, we know that it is 4 moles of ammonia for every negative 906 kilojoules. So remember, that was our ratios we were talking about. We could take each one of these over the negative 906 kilojoules. Now this problem says to calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So again, keep this in mind here, 155 grams. So the first thing that you should realize is that since this is in grams and this is in moles, that we need to do a mole to gram, or gram to mole conversion. Okay, gram to mole conversion. So let's go ahead and get that set up. So we have 155 grams of ammonia. We need to do a gram to mole conversion, so 1 mole of ammonia, and we'll need to calculate that value out or look it up, whichever the case may be. And so we get 17.031 grams of ammonia for every 1 mole. Now, next step, we've got a moles, and we know that only 17 grams is 1 mole. Well, we have 155 grams, so we're obviously going to have more moles than just 1. But we're looking for the heat energy that is associated with this. And so I now know that for every 4 moles of ammonia, I'm going to get a negative 906 kilojoules. And so my answer that is left is now kilojoules. And so I should be ready to go and do my calculations. So I'm going to go ahead and just multiply across the 155 times negative 906. And I get that to be, well, let's see, that would be 140,430. And that's kilojoules. And then I'm going to go ahead and multiply across the denominator. And I get 68.124. Now, we've talked about this over and over about whether or not you have to show that. I like it just because I can see if you punch something in the calculator wrong. If that is not something you want to do, that's okay. Just make sure that you are very careful in your work. So now we're just going to go ahead and divide those two numbers. And I get 2,061.389. Now, where you kind of take this out at this point is kind of up to you, because we do need to go back in and look at our significant digits. And so in our problem here, we only have 3 significant digits. That means I can only go 3 significant digits in my answer. So that would be right here, which means that the last 0 is going to, or the last 1 is actually going to round to a 0. So again, significant digits is 3. So this would be 2060 kilojoules. But anything, as I've told you before, that is in the thousands or above should go to scientific notation. So 2.06 times 10 to the third kilojoules. And then that makes it a lot easier here to see your 3 significant digits. Okay, so that is an example of how to go from grams to the amount of heat energy associated with a reaction. Again, it is fairly straightforward and fairly easy. I guess I did forget one thing on here because I dropped my negative. I apologize for that. So it is a negative value. And so if you go back to what we discussed prior, so the question is that an endothermic or an exothermic reaction? And if you'll remember, a negative, the system gave off energy. So this is an exothermic reaction. Okay, exothermic. Okay, so if you have any questions, please don't hesitate to ask. Over this, you're going to be doing some of these practice problems over this material. And if you need more help, I do have a second video that just works through more of these examples. If you feel great about this topic, then go ahead and go to your worksheet. But again, if you at any time struggle, then go to the second video and watch some more examples. And that's it for today. So signing off, Mr. Schaaf's classroom.